Yesterday we did a demonstration with standing waves. I attached a string to a mechanical wave generator at one end and to a desk leg at the other end. We sent down a continuous wave from the mechanical wave generator. As it hit the boundary between the string and the desk leg, it reflected. When it reflected, there was a wave going down still and then a wave coming back. Those two waves interfered with each other. Now, at most frequencies, and I could change the frequency of the wave yesterday. At most frequencies, the interference pattern appeared to be random. It wasn't random. We could have predicted exactly what the interference pattern would look like by that superposition principle that we did earlier this week. Remember, add up the number of blocks above the axis, add up the number of blocks below, and add them all up, right? We could have figured out what it looked like. We just didn't. Okay? We could have, and it would have given us the pattern that we observed yesterday. But the ones that we wanted to focus on were the ones that appeared to not be random, the ones that appeared to be special, the ones that we call standing waves. Standing waves are waves that appear to be standing still. The first one that you saw yesterday was like this. It appeared to be standing still. The second one that you saw yesterday was like this. Again, it appeared to be standing still. The third one that you saw yesterday was like this. Again, it appeared to be standing still. It happened as a result of these waves that were going down from the source to the boundary at the other end, reflecting and then interfering at very specific frequencies to look like one of those. Now, what frequencies would they occur at? Well, we said there were very specific frequencies. They correspond to the resonant frequencies or the natural frequencies of the string. I think for you guys, the first one occurred at around 5 hertz. Do you guys remember the numbers? I think it was somewhere around 5, wasn't it? The second one would have occurred around 10, and the third one would have occurred around 15, and then 20, and so on and so on. They correspond to the natural frequencies of that string. Now, the diagram that I've got on the board here isn't fantastic. It's more circular than sinusoidal, but you get the idea. Okay, we get a wave that looks like this, the solid line wave, and then you've got this dotted line wave down here that kind of complements that. We know that the string is going back and forth between the bottom and the top, But there's certain points that we call nodes where the string isn't moving at all. There's 5 nodes, 1 at both ends, and then 3 in the middle. At these nodes, we have complete destructive interference. And the string isn't going up or down because the crests and troughs are canceling each other out perfectly at that point. The antinodes, on the other hand, where you have the high spots or the low spots, or where we have complete constructive interference. So you're making a bigger wave, a bigger crest, a bigger trough. It looks like we've got a crest and a trough at the same time. We don't. Okay, it's here, or it's here, or it's somewhere in between. It can't be in both places at the same time. But remember what a standing wave is. It's a wave that looks like it's standing still, appears to be standing still, because our eyes can't register fast enough. There are parts called the nodes that are standing still, and then there's parts called the antinodes that appear to be standing still, but really are going back and forth between the bottom and the top. A little bit more here. We've already talked about this, but it's just formally writing it down here. The part of the wave that is still, the part of the wave that's not moving, okay, we established it up here as the part that experiences destructive interference. We call that the node. And the part of the wave that is moving up and down, but appears to be standing still, is what we call the antinode. Okay, the node, remember, we have destructive interference. The antinode is where we have constructive interference. So now it comes time that we have to draw out the standing waves, the different possibilities of standing waves, and figure out an equation that will describe these standing waves. In other words, if we see this, we have to be able to predict what frequency that will occur at. Yesterday we saw what frequency it would occur at, but we just kind of did it experimentally. We just kept turning the dial up until the standing wave occurred. We need to be able to predict at what frequency that's going to occur at. Maybe you're a musician. Maybe you make musical instruments. That's what you do for a living. You make guitars, you make pianos, you make musical instruments. You need to be able to figure out what the length of the guitar string needs to be in order to produce this pitch. Or you need to be able to predict what pitch this piano string will produce. We need to know something about the mathematics of standing waves to do that. So let's take a look at this page. There's 4 diagrams that we're going to draw on this page. The first diagram is going to be the first standing wave that we see, which is that one where we have one antinode and 2 nodes. A node at both ends, an antinode in the middle, and the string is going back and forth between the bottom and the top. This one doesn't even really appear to be standing still. You saw this yesterday. You could physically see the string going up and down, right? It was kind of a unique pattern. There was waves going down and waves coming back, and it didn't look like that, but you could still see the string going up and down. The second one that we saw, we could see the movement a little bit less. It looked something like this, where you had 2 antinodes and 3 nodes. The third one, we had 3 antinodes and we had 4 nodes. And then the next one, of course, we had 4 antinodes and we had 5 nodes. And you could keep going, right? We went up to, I don't know, 20 or 30 antinodes. Say we had 30 antinodes, we would have had 31 nodes. Next, assuming that this is the same string attached to the mechanical wave generator and the desk leg at the other end, or one end of the guitar string and the other end of the guitar string, assuming it's the same string in all 4 cases, we're going to define the length of that string as L in all 4 cases. 20 centimeters, 50 centimeters, 10 meters, whatever. The length of that string is L. Next, and this is kind of the crux of it, this is the hardest part of it. We want to define the length of the string in terms of the wavelength. Let me draw a wave here. Over here on the side. Okay, there's a whole bunch of different sections of a wave. We want to look at each of these and define how much of a wave we have. In other words, the length of it is equal to how much of a wave. Right here, we're going from equilibrium up through the top down to another equilibrium. So in other words, we're going like this. Can you tell me how much of a wave that is? Is that a whole wave? Is that a half a wave? Is that 3/4 of a wave? Is it 2 waves? How much of a wave have I just penciled in red there? It's a half a wave. So we're going to say the length of this string, in this case, is half of the wavelength. Now I'm going to rearrange that to solve for lambda, because ultimately that's what I want. Lambda is equal to 2 times L. It's just easier to do it in terms of L first. L is equal to 1/2 of lambda, and then to rearrange it. Next one. Next one. We're going from the start up through here, down through here, all the way to here. How much of a wave is that? Alice, how much of a wave is that one? Half a wave? Going from here all the way back to here, this is going to be good. It's going to be a whole one. So we're going to say L is equal to lambda. Now, we don't really need to rearrange that because L is lambda, lambda is L, same deal, right? I just want to keep it nice and uniform. Solve for L in all the cases. Next one. Next one, we're going right through here, which is what we already have, but then we're going another half a wave right here, right to there. What's that? L is equal to what now? 1 wave, 2 waves, 3 waves, a half a wave? It's 1.5. Now, I'm going to write it as L is equal to 3/2 lambda. Yeah, but there's no reason, Sam, why you couldn't write 1.5 or 1.5. You're going to see why in a few minutes. I've written it as 3/2. But again, it's not wrong to do it 1.5, 1.5 as an improper fraction. Whatever, doesn't matter. We're going to rearrange that. Lambda ends up being equal to 2 goes up by multiplying, 3 goes down by dividing. becomes 2/3 L. And finally, the last one, we're going all the way over to here now. How much of a wave is that? How much of a wave we have there, Phil? 3 waves? Going from here to here, that's one. Going from here to here, that's another one. 2 waves, good. So we're going to say L is equal to 2 lambda, or lambda, if I take that over by dividing, is equal to a half of L. Let's get rid of this ugly picture over here on the right side now. And now let's write down for each of these the wave equation. V is equal to F times lambda. But usually we're going to rearrange that in this case to solve for F, V over lambda. So F is equal to V over lambda in all 4 cases. All right, that's the universal wave equation. We call it universal because it's always valid. No matter how long the string is, no matter what the frequency is in terms of the length, or no matter what the length is in terms of the frequency, or wavelength, or whatever. Let's sub in for lambda 2L. We're going to say in this case F is equal to V over 2L. Right, lambda becomes 2 times L, F becomes V over 2L. Let's sub in L here for lambda. So we're going to say F in this case is equal to V over L. Let's sub in 2/3 L. We do this, it becomes F is equal to V over 2/3 L, which we want to simplify that a little bit. Okay, divide by 2/3, it's the same thing as multiplying by 3/2. And finally, the last one, F is equal to V over lambda, V over 1/2 L, yeah. Right, subbing in again, 1/2 L for lambda. Let's just simplify that a little bit. V over 1/2 L is the same thing as saying V times 2 over 1L. So it becomes 2 times V over L. Now, you might not see a pattern quite yet, but I'm going to point it out. F is equal to V over L is what we call the fundamental, or the first harmonic. That's the first resonant frequency of a string, or of a steel plate, or of anything that's the same at both ends, fixed at both ends. The first harmonic, the first standing wave that would occur, the first resonant frequency of that object. A bridge, right? You guys watched the Tacoma Narrows Bridge vibrating in the wind. You saw it going up and down and up and down. Okay, the first harmonic of that standing wave, the first standing wave, the first resonant frequency that was produced was V over 2L. It would have been very easy to calculate what frequency that would occur at. All you'd need to know would be the speed of the wave, the length of the bridge, and you'd find the resonant frequency of that bridge, the first harmonic, the first resonant frequency of the bridge. This one, take a close look. This is V over 2L. V over L, is that not the same thing as saying 2V over 2L? That's the same thing. 2V over 2L, V over 2L, 2V over 2L, 3V over 2L, and 2V over L is the same as saying 4 over 2V over L. V over 2L, 2V over 2L, 3V over 2L, and 4V over 2L. Basically what we're saying here is that this one is twice the first one. We're going to call that the second harmonic because it's twice the value of the first harmonic. This one is 3 times the value of the first harmonic, so we'll call it the third harmonic. And this one is 4 times the value of the first harmonic, so we're going to call that the fourth harmonic. The second harmonic is twice the first. The third harmonic is 3 times the first, and the fourth harmonic is 4 times the first harmonic. So what does this all mean? Okay, what does it all mean? Well, the most important one, the one that we usually look at, is this first harmonic. You pluck a guitar string, there's all kinds of sounds produced. There's hundreds of different frequencies of sounds produced. But you don't hear hundreds of them because the vast majority of them die out. They die away very, very quickly. Why? Why do the vast majority of sounds in a guitar string die away when you pluck the guitar string? I'll give you a hint. Because they're not resonant frequencies. They're not natural frequencies of the string. What lasts? What stays around? What sound do you hear? The resonant frequency of the string, which corresponds to largely the first harmonic, maybe with some second harmonic in there, or maybe some third harmonic in there as well. It makes some sense? Everything has a natural frequency at which it wants to vibrate. The bridge, the meter stick that we were talking about with resonance the other day, the pop bottle, the water bottle, the guitar string, a string in a piano, okay, the clarinet has a natural frequency at which it wants to vibrate. This is the first resonant frequency of a guitar string or anything like that. Calculate its value, V over 2L. The speed of the wave divided by 2 times the length of the string. There are other harmonics or other standing waves or other resonant frequencies sometimes mixed in there. The second harmonic, the third harmonic, the fourth harmonic, and so on. Now, I was chatting with some people in the last class about music, and I don't know a whole lot about music, about the theory of music. I know something about the physics of music, but not so much about, what do you call this note and that note and whatever. I was really good at recorder in grade 4, okay, when they had pictures of where you're supposed to put your fingers as opposed to having to actually read notes. And I don't want to brag, but I have also managed to figure out all by myself on a guitar the first 6 notes of Jingle Bells without anybody's help whatsoever. I can't get beyond the first 6 notes. Okay? I'm still working on that, but I'm really good. I've nailed those first 6 notes of Jingle Bells all by myself. I don't know a lot about the theory of music, notes and so on, but I know about the physics of music, okay? This is the first harmonic. If you double the first harmonic, you get the second harmonic. If this was a C note, this would also be a C, but 1 octave higher. This would also be a C, but 1 octave higher, and so on and so on. Does that make some sense? If you know anything about music, that might make some sense. If you know anything about music, it might make more sense than it does to me. When you pluck that guitar string, you hear this one. But you might also hear some of the other ones mixed in with it. If you blow on the top of a water bottle, you might hear the first harmonic, but you might hear the second harmonic, the third harmonic mixed in with it. This is kind of ugly, eh? There's a lot of stuff on the board here right now. There's good news with this. Okay, good news is the pattern that's formed here. The second harmonic is twice the first harmonic, the third harmonic is 3 times the first harmonic, and so on. Really, all we have to be able to do is this one. Because if you can do this one, and you're dealing with a problem with the third harmonic, just recognize that the third harmonic is 3 times the first one. Or the fourth harmonic is 4 times the first one. You don't need to derive all of these equations. You need to be able to derive this one. And you got to be able to multiply it by 2, or by 3, or by 4, as the case may be. All right, I want to do an example, and I'll show you how easy it actually becomes here, okay? So the first one. First example today. In fact, the only real example today. We'll do a couple more practice questions as you guys are working, but the only real formal example that we'll do today is a 25 centimeter long string is set in vibration. I'm going to circle this centimeters because I don't want to keep it in centimeters. The speed of the wave through the string is 500 meters per second. What are the first 3 possibilities for harmonics in the string? So in other words, what's the first harmonic? What's the second harmonic? What's the third harmonic? Let's draw it out. I'm going to draw it out because the equation that I derived here a few minutes ago doesn't appear on my data sheet. I got to be able to figure it out every time. This is L, the length of the string. And I know the length of this is 1/2 of lambda, and therefore lambda is equal to 2 times L. I know that F is equal to V over lambda, and I know that therefore F is equal to V over 2L. This is the first harmonic. Right, the first sound, the first standing wave, the first resonant frequency that would be produced. Its value is going to be the speed of the wave, 500, divided by 2 times the length of 0.25 meters, which gives me 1,000 hertz. So if this is a guitar string or some other musical instrument that has a string and you pluck that string and you set it in vibration, there's going to be hundreds of frequencies produced. Most of them die out because they're not resonant frequencies. This one won't die out. You'll hear 1,000 hertz. It will vibrate back and forth at 1,000 hertz. What other one might you see? What other mode of vibration might be set up in this string as well? The second harmonic, which is twice the first harmonic. What other one might you see set up? The third harmonic, which is 3 times the first harmonic, or 3,000 hertz. We could have, for this one and this one, derived these equations. But why would we? Right? Why would we? If we figure out the first one, why wouldn't we just multiply it by 2 to get the second and by 3 to get the third harmonic? All right, guys. I'm going to give you a worksheet in just a moment, and there's a number of questions on that worksheet, 4 pages in fact. The first 2 pages go up to question number 11. I'm going to ask you guys to do the first 8 questions, please, on that worksheet. All of them involve standing waves, what we've just been doing, but standing waves where we have 2 fixed ends, like a guitar string, like the piano. Okay, same deal with the piano. Like anything else where both ends are attached, a harp or anything like that.